Analytical Chemistry 1, Lesson 33. Proteins are some of the critical molecules that make up life. Proteins perform many essential roles. They catalyze reactions, they manage DNA replication, they respond to stimuli, they provide structure to cells, they transport molecules from one site to another. Their structure is key to their performance, and their primary structure consists of a linear sequence of amino acid molecules connected in series. The most fundamental structural feature of an amino acid is that it joins a carboxylic acid group to an amine group. Each amino acid differs from the next by the nature of the substituent on the central carbon atom. There are 20 common amino acids, and proteins primarily differ from one another by the sequence in which they are assembled. Our interest in this course, however, focuses on the fact that both the carboxylic acid and amine groups can exchange protons with the surroundings. They both have acid-base character. Amino acids are diprotic acids. They have two sites that can donate or accept protons. Each site has its own Ka value. The acid's value is always much greater than the ammonium ion's value. Each substituent affects the details of the bond strengths and intermolecular interactions differently, so for each molecule, the Ka for the acid is different and the Ka for the ammonium ion is different. Also, 7 of these amino acids have acid-base sites on the substituent groups as well. It has its own value for Ka, and that molecule is a triprotic species. In very acidic solutions, both the acid group and the amine group have a proton attached. The molecule carries a net positive charge. The amine group becomes the ammonium ion. In very basic solutions, both protons have been removed. The carboxylic acid group is negatively charged, having lost its proton. Throughout the rest of the range of pH, you might think the molecule is neutral. While it is part of the time, the form where the proton is off the acid and a proton is on the amine creates what is called a zwitterion. While its net charge is 0, it is stabilized by solvent interactions to favor the zwitterionic form over the neutral species. In the gas phase, it's the neutral species that dominates because of the absence of these additional stabilizing interactions. In most situations, the zwitterion is the most common species encountered. From just below pKa1 to just above pKa2 is the general range wherein this equilibrium between the neutral and zwitterionic forms operates. The pKa of the carboxylic acid moiety is around 2.15 for all of the amino acids, while the pKa for the ammonium group is around 9.2, though they seem to have a bit wider spread of values. For those with a third acid-base group, its pKa ranges across the spectrum from some very acidic around 4, while some are very basic around 11. We will focus first on the diprotic species. That means we need to deal with two reactions. The first, acid dissociation, takes the fully protonated species, releases a proton, and forms the neutral species, which in reality is mostly in its zwitterionic form. The equilibrium constant here is Ka1. I am using the shorthand for the molecule as just AA for amino acid. These ideas apply to all of them. Similarly, the second acid dissociation takes this zwitterionic species and releases another proton to form the negatively charged species, with its equilibrium constant being Ka2. Note how the neutral species, the zwitterionic species, is the conjugate base of the fully protonated species. At the same time, it is the conjugate acid of the fully deprotonated species. The molecule can behave in one case as an acid and in another as a base. Molecules that can do that are said to be amphiprotic. To recall how we showed that the product of an acid dissociation constant with the base hydrolysis constant between a conjugate acid-base pair was equal to the water ionization constant. Well, the same thing happens here, but make sure you employ the Ka and Kb for the same reaction. If we start with the fully basic species, we allow it to react with water to reproduce the neutral zwitterionic species whose equilibrium is given by Kb1. Further reaction of the neutral species with water produces the fully protonated species with Kb2. Note the following relationships. K1 Kb2 is equal to Kw, and Ka2 Kb1 is equal to Kw. Remember to use the right equilibrium constants together. You can obtain an amino acid in any of its three forms, the fully protonated, the fully deprotonated forms, or the neutral zwitterionic form. Let's consider for now the simplest amino acid, glycine. The substituent R that characterizes glycine is simply a hydrogen atom. It is diprotic with two Ka values, pKa1 of 2.350, and pKa2 of 9.778. Glycine hydrochloride is the salt of the low pH species. If you add it to water, it is just adding a weak acid to water, operating with a pKa of 2.350. But what about the other acidic proton? Does it affect the solution pH? H2Gly+, now I'll use this shorthand for the glycine molecule, is a weak acid, though it's a strong weak acid, but it only partially dissociates upon solvation. Its conjugate base, H-Gly, and I write it here as if it were neutral, but remember that its most common form is actually the Zwitter ion, which I guess we could write as plus H-Gly minus, but I'll just stick with H-Gly and you remember the rest. The base that is conjugate to H2Gly+ is also a weak acid that is conjugate to the fully deprotonated species Gly-. It is characterized by the pKa of 9.778. If H2Gly+ is a weak acid and only partially dissociates, then H-Gly must be a really weak acid that will hardly dissociate at all. And also reflect on Le Chatelier's principle. If the first dissociation is pumping hydronium ions into the solution, those hydronium ions are, in the second reaction, going to drive it in reverse towards H-Gly and inhibit its dissociation. Bottom line, we can treat the addition of the fully protonated species as if it were a monoprotic acid. We can draw upon our previous mathematics then. Here's an example situation. What is the pH of a 25 millimolar solution of glycine hydrochloride? Just use the quadratic solution for a weak acid. The pH is 2.067, quite acidic. It's much more acidic than a solution of acetic acid, for instance. We might ask about the concentration of the other species. The pH is so acidic that the hydroxide concentration must be very low, so any hydronium that comes from water dissociation must be very small, and we can equate the H-Gly conjugate base concentration to the hydronium ion concentration. And subtracting from the formal concentration gives us the undissociated H2Gly+ concentration. This is possible because we consider the Gly- concentration to be negligibly small. Finally, we note that the fractional dissociation is about 34%, but another species present is hydroxide. That suggests its concentration is low, and very low in fact, and finally the fully protonated form Gly-. Because we have already asserted that the hydronium ion concentration equals H-Gly concentration, just look at the Ka2 expression, and we see immediately that Gly- is 1.67 times 10 to the minus 10 molar. What about at the other end of the pH scale? We can add sodium glycinate to water to form a solution that is formally 0.025 molar in the glycinate anion. Hydrolysis of the glycinate anion produces its conjugate acid, the neutral Zwitter ionic form H-Gly, which is of course also the conjugate base for the fully protonated form. But as in the acid case, negligible association will occur and we treat the base as a monoprotic base. Find Kb1 by dividing Ka2 into Kw to get 6.03 times 10 to the minus 5. Use the quadratic solution for the hydroxide concentration. It is 1.2 times 10 to the minus 3 molar. Divide back into Kw to find that the hydronium ion concentration must be 8.39 times 10 to the minus 12 molar, and therefore the pH is 11.076. We make the same assumption as before, that there is negligible reaction of the H-Gly to produce any H2Gly+, so that the H-Gly concentration must be the same as the hydroxide concentration. Remaining Gly- is found by subtraction from the formal concentration. Note also that the fraction association this time is only 4.8%. The acid form is more acidic than the basic form is basic, but not by much. And finally, what about the H2Gly+ that is produced in what we anticipate will be a very small quantity? First, find Kb2 from Ka1 and then recognize, as before, that since OH- equals H-Gly, then H2Gly+ must equal Kb2, which equals 2.25 times 10 to the minus 12 molar. So now what about glycine itself? We can also obtain a bottle of glycine and introduce that into some water for solvation. What happens then? Well, the neutral or the zwitterionic glycine molecule is amphoteric. It behaves as both an acid and a base, as Ka2 or Kb2 respectively. The complication for us this time is that both reactions need to be considered. We need to pursue the systematic approach to solve this situation. We can write out the charge balance equation. Use the two equilibrium expressions to replace the two glycine species in the charge balance. Now, most commonly, the data regarding the equilibrium constants is presented in tables as Ka1 and Ka2. We have to fiddle with Kw to find a Kb value. So it would be of value to switch the Kb2 for a Ka at this point. Recall that Ka1 equals Kb2 times Kb2 equals Kw. So substitute Kw over Ke1 for Kb2. At the same time, let's replace hydroxide for hydronium ion. It also involves the Kw, of course. Well, here's the replacement. And we can, of course, cancel the Kw's found in the second term. Continuing the derivation, we have this version of the charge balance equation. Let's get rid of the denominator terms. Multiply throughout first by H plus, then by Ka1. Our expression now looks like this. Factor out the H plus squared, and finally we obtain an expression for the hydronium ion concentration. Now, the problem's not quite there yet. We still need to know how to determine the actual glycine concentration, H-gly. The rigorous answer lies with the as yet unused mass balance equation. The formal concentration must be the sum of the concentration of the three glycine species, glycine itself, along with the glycinium ion and the glycinate ion. Replace the expressions for the two ions with expressions from the two equilibrium constants and gather terms together. We now have two equations and two unknowns. We can combine them and expand it out into a polynomial. It'll prove to be a fourth order polynomial, and solve for the roots. Now, I'm not going to do that here right now. Another approach is to use the successive approximation using goal-seek. It is set up quite nicely to do that. Have it vary H-gly, calculate H plus, and determine F, and continue until the result equals the actual value of F. When the formal concentration is 0.025 molar, we get H plus equals 7.967 times 10 to the minus 7 molar. The pH is 6.099. We can now calculate back to find the concentration of each of the glycine species. First, rearrange the mass balance equation to find H-gly, then use the two substitutions used in the mass balance for the two ionic species. We obtain these three values. Now look at these numbers. Can you draw any conclusions from them? Well, the first thing we notice is that H-gly concentration is almost identical to the formal concentration. This means that the weak acid reaction to form the glycinate ion and the weak base reaction to form the glycinium ion, that both of these reactions hardly went forward at all. Perhaps we should have considered that to have happened from the outset. The two equilibrium constants for the reactions, which are Kb2 and Ka2, are very small, 10 to the minus 12, 10 to the minus 10. We should expect very little reaction from them. The first approximation is that H-gly is equal to F. A single calculation then gives the hydronium ion concentration. Let's compare this with the exact solution. The agreement is excellent. The extra computational effort's hardly worth it at all. This is a good approximation. With some further restrictions that are commonly met, we can find an even simpler approximate solution. Second approximation is if the formal concentration is reasonably large and reasonably depends upon the magnitude of the equilibrium constants, then Ka2 H-gly is very much greater than Kw, and the first term in the numerator cancels out. And additionally, if H-gly is very much greater than Ka1, the denominator is just H-gly, which cancels the numerator, and to give us the square root of the product of the acid dissociation constants. Take the logarithm of this expression, and you see that it is equivalent to saying that the pH will be at the average of the two pKa values. This is a more substantial approximation, but it is still very good. It predicts a pH of 6.063 rather than 6.099. But with all the uncertainties associated with the measurement of pH, this is still a very reasonable approximation. When do these approximations fail? Not often, actually, but they do become weaker when the formal concentration is too low or the two pKa values come too close together.